Good morning, ladies and gentlemen, and welcome to the Department of Physics. I'm Paolo Radaelli. I'm the Dr. Lee Professor of Physics, and I'm here to introduce the lecture series and this particular lecture. I'm going to share the screen. So this is the 61st Cherwell Simon Memorial Lecture, and these lectures are given in honor of Friedrich Lindemann and Franz Eugen Simon. Friedrich Lindemann, first Viscount Cherwell, became Dr. Lee's Professor of Experimental Philosophy in 1919 and Director of the Clarendon Laboratory. And he was one of the main scientific advisors to the British government, in particular to Winston Churchill, since the days when he was writing books and opinion pieces for newspapers and magazines. Francis Simon graduated in Berlin in the research group of Walter Nernst on low-temperature physics, in particular in the third law of thermodynamics. He was invited by Friedrich Lindemann to join the Clarendon Laboratory, which he did in 1933. He became a reader in thermodynamics in 1936, and later Dr. Lee Professor of Experimental Philosophy and head of the lab in 1956, sadly 1 month before his death, and I think his daughter is here in the audience with us. The Cherwell Simon lectures have been given continuously since 1960, and this slide shows the lectures since 2010. Many Cherwell Simon lectures have been highly distinguished, and we had many Nobel Prize both in recent times and earlier on. The last lecture was given in 2019 by Eleanor Prile, and unfortunately the 2020 lecture was cancelled due to COVID. It is a great pleasure for me to restart the series with what is truly an exceptional speaker, which is Professor Fabiola Gianotti, Director General of CERN. As you know, CERN is the most successful multinational scientific enterprise ever, and intense science diplomacy is required to ensure its success. Italy and the UK have always worked side by side in this and many other scientific areas, scientific endeavors and areas of science. It is for this reason that I've asked Massimo Carnelos, who is the head of the economic office of the embassy of Italy in London, to say a few words of welcome on behalf of the ambassador. I should say that the embassy has collaborated in the organization of this event and promoted this event, and I know that many of you have joined through this route. Massimo.
Thank you, Paolo. I hope you can hear me.
Yeah.
And good afternoon to all, and thanks for connecting today. Many thanks to the co-organizers, Department of Physics of the University of Oxford, and particularly thanks to you, Paolo, for all this. Well, it is a great honor for me to welcome Professor Fabiola Gianotti, Director General of CERN. I'm here to bring the greetings of the ambassador of the Italian embassy in the UK, and let's say about all Italians from all sorts here in the UK. I feel enormously humble to open these lectures. I mean, given the international standing and prestige of today's special guest. And I don't want to take much of your time, as most of what I'm going to say is nonsense comparing to what we are going to hear in a minute. From my very personal perspective, Fabiola Gianotti has the enormous privilege of having dedicated her life to probably the most noble and fascinating disciplines of all, a discipline that embodies the human search for truth, from the early speculations of the pre-Socratic philosophy in ancient Greece to the most advanced researches conducted by institutions like the CERN she leads today. Physics is our way to interrogate the mysteries of the universe, and in a way not to interrogate ourselves and our place in this whole, from the smallest particles of the matter to the arcane secrets of the cosmos. of which we still know only a fraction of. Allow me also to say how proud we are as Italians for Professor Gianotti, and together with her, all other distinguished Italian professors, scientists that work in Italy and overseas. In Italy, as you might know, many of you might know this, we often complain of the brain drainage, which is definitely an issue that we have not been able to tackle properly yet. I would add that the issue is not so much about scientists leaving, but about scientists coming back with their newly acquired international background, as well as attracting foreign scientists. I conclude by pointing to the importance of this event that we sponsor with enthusiasm to keep alive the scientific cooperation between Italy and the UK. Science is what more than anything else brings people together, regardless of the borders, language, religions, identities, cultures, and CERN symbolize this. And science stands high on the list of priorities and actions we have as Italian government to keep the Italian-British relations rich, vibrant, and growing post-Brexit. So thank you to you all, and I believe I have to give the floor to Professor Gianotti. Thank you.
Actually, before I do that, I will allow, I give the honor to introduce Fabiola Gianotti to Daniela Bortoletto, who is the head of the particle physics department, sub-department here at Oxford Physics. Daniela.
Thank you. The daughter of a geologist from the Piedmont region of Italy, who taught us the love of nature, and a mother from Sicily who was passionate about music and art, Fabiola Gianotti studies the classics and piano before receiving a PhD in experimental particle physics from the University of Milan in 1889. Since 1994, she has been research physicist at CERN, the European Organization for Nuclear Research. She has made significant contributions to the building of the Atlas detector, developing the Atlas collaboration, and analyzing the data delivered by the Large Hadron Collider. From 2009 to 2013, she was a spokesperson of the Atlas collaboration, which includes about 3,000 physicists from 38 countries. On July 4th, 2012, Fabiola presented the Atlas results on the search for the Higgs boson in an historic seminar at CERN. This event marks the announcement of the long-sought discovery of the Higgs boson by the Atlas and CMS experiments, a great triumph for both theoretical and experimental particle physics. Dr. Gianotti is an honorary professor at the University of Edinburgh, a member of the Italian and the US Academy of Sciences, a foreign member of the Royal Society, and a member of the Scientific Advisory Board of the UN Secretary General. She has received honorary doctoral degrees from many universities, including Uppsala, McGill, Oslo, Edinburgh, and EPFL. She has received the Special Fundamental Physics Prize of the Milner Foundation in 2012, the Enrico Fermi Prize of the Italian Physical Society in 2013, the Medal of Honor of the Niels Bohr Institute in Copenhagen in 2013, and the Cavaliere di Gran Croce dell'Ordine al Merito della Repubblica Italiana. She has been included among the top 100 most inspirational women by The Guardian, ranked 5th in Time Magazine Personality of the Year in 2012, included among the top 100 most influential women by Forbes magazine, and considered among the leading global thinker of 2013 by US Foreign Policy magazine. In 2016, she became the first female Director General of CERN. She was elected, unprecedentedly, I think, to a second term in 2019, and she has just started a second term as Director General in January of this year. Gianotti strongly believes that we need to break down barriers between the arts and science. For her, an accomplished pianist, science and art are not different things. They are both the highest expression of creativity, of curiosity, of the ingenuity of humanity. She has been a great advocate for science and the unifying aspect of science. She has said, science has no passport, no gender, no race, no culture, no political party. Science can play a leading role in connecting people and creating a shared future in a fractured world, because science is universal and unifying. It is a true pleasure for me to welcome her to Oxford for the 61st Cherwell Simon Memorial Lecture, to talk about scientific research and much more at CERN. Welcome, Fabiola.
Good evening, everyone, and I hope you can hear me well and that you can see my slides. And first of all, it's a great honor to be invited to give such an important and prestigious lecture. And also many thanks for the very nice introduction from Paolo Radaelli, Massimo Carnelos, and Daniela Bortoletto. I'm also very pleased to have the opportunity to talk about CERN, which is not only a center of scientific excellence, but much more than that. And I will try to stress the role of CERN in all its facets. So let me first remind you that CERN is the largest laboratory for particle physics in the world. It's an intergovernmental organization based in Geneva. Our primary mission is science, namely fundamental research in particle physics. And particle physics is the most fundamental of all sciences because it studies the smallest constituents of matter and of the universe. And these activities, this research has been awarded over the years by several discoveries. The last one is the Higgs boson and Nobel Prizes to scientists working at CERN. CERN is also a driver of innovation because the scientific goals are so ambitious that we, in order to accomplish them, we need to develop very, very complex object instruments, particle accelerators, particle detectors, and computing infrastructure. And therefore also to develop many cutting-edge technologies in many fields, from superconducting magnets to data, big data, fast electronics, vacuum, cryogenic, etc. And these technologies are transferred to society for free. They're available to everyone. Perhaps the most important and most known example is the World Wide Web, which was developed by CERN team Berners-Lee when he was a CERN staff in 1989, and then made available in 1993 for everyone to use and develop. But I will also give other examples of the impact of CERN on society. Another important pillar of our mission is training of tomorrow's scientists and education of the general public or of high school students and teachers, etc. And last but not least, CERN is a concrete example of collaboration across borders because it attracts some 18,000 scientists from all over the world. More than 110 nationalities are represented. CERN was founded in 1954 by 12 European states, and the UK and Italy are among the founding members. So this was in the aftermath of World War II, and the goal, actually, there were two main goals for the creation of this new laboratory. One was to bring back scientific excellence to Europe. During the war, many brilliant minds and many brilliant scientists had moved to other countries, other continents. And the second goal was to foster and promote peace in Europe through science. So the visionary founding fathers, I must say fathers because they were all men, at the time understood, first of all, that the economic renaissance of Europe also goes through science, but also that science is a very strong glue. And this is still very true nowadays, and I will give you, for example, later on. Today, CERN has 23 member states, 9 associate member states and 6 observer states. Our budget is 1.2 billion Swiss francs per year. And if you want to use more friendly units, this corresponds to 1 cappuccino per year per citizen in the member states countries. And this budget is contributed by the member states in proportion to their net national income. And the UK actually is the second largest contributor after Germany, with some 15% of the budget, so some 174 million Swiss francs. This budget is used to conceive, to develop, to build and to operate the scientific and technical infrastructures that are used at CERN by particle physicists coming from all over the world. And here in this slide, you can see the distribution of all the CERN users, so scientists from all over the world involved in CERN activities. You can see that a large part of them come from the member states here in dark blue. Some also from non-member states like the US, for instance, or Russia and Japan and China. These, of course, are countries that are on the front line of science and technology, but you can also see that some of our scientists come from countries like Nigeria, Mongolia, Madagascar, Azerbaijan, really not countries that are leading in terms of science and technology. So in this case, the role of CERN and the CERN community is to build capacity, and so to help these countries close the gap with the more developed countries. You can also notice that some of these scientists come from countries like Israel and Iran that are not really the best friend of each other. And actually here, they all work together, animated by the same passion for science. So this is really an example of a truly global collaboration across borders and a truly inclusive endeavor. The UK participates and contributes with some, say, 1,000 scientists. Some of them are CERN employees of British nationality. Some others are scientists from UK institution of British nationality or other nationalities. Now, you may think that these scientists are a bit, you know, old and boring people, but actually, if you look at the distribution of the age of our scientists, you see that the peak is at 27. And at any given time, we have more than 3,000 PhD students in the experiments that are carried out at CERN, and about 50% of our population is below 40-45. So really, it's a very young population, and these young people are the driving force of the lab. The female fraction is still a bit on the low side. We are at the level of 20%. However, there has been great progress, because when I came to CERN in 1994, female scientists, so physicists and engineers, we were at the level of 8%. So there is still a long way to go, but there has been a lot of progress. Now, only a small fraction of these young people remain in research in particle physics, because the number of jobs in research is limited, but also because they may want to do something else in their life. So where do the others go? Well, about half of those who leave the field go to stay in the public sector, in other organizations or in academia, and half go to industry, private sector. So you can see telecommunication or engineering, computing, etc. And we've made recently a survey of the people who leave CERN. And we have asked them, what are the skills that you learn at CERN that have been, first of all, fundamental to find your current job, a job at the level of your talent and expectation, and also that you consider very important for your current job? And the answer was, of course, first of all, programming, so learning modern technology, in particular in software development, and the second one was working in an international environment. So because we have so many young people, education is one of our important goals, and actually our mission. It covers, education and training covers various activities for young researchers and or for students in our field, so physicists, engineers, computing science, scientists. And we are running now, we've been running for many years, for decades, schools for them, starting first in Europe, then moving also to Latin America, to Asia, and recently we've been teaming up with other institutions in Europe and beyond to run schools in Africa. And you see, over the past years, we've been to Ghana, Senegal, Rwanda, and Namibia, again, with the goal of building capacity there and helping the young generation there prepare a professional life in science and technology. But we also have many initiatives for the general public and for the high school students and teachers. In particular, we run a very successful high school teachers program, which attracts typically 1,000 teachers every year, of course, in a pre-COVID period. And until now, the program has attracted some 13,000 participants. These high school teachers come to CERN during the summer and spend with us a couple of weeks and gets a complement of training in the hands-on and modern experimental physics. And every year, of course, again, in the pre-COVID period, we were able to attract something like 150,000 visitors. We received 300,000 requests for visit, and we can only satisfy half of them. Most of them are high school students, and it's not just a local tourism. 80% of our visitors come from more than 700 kilometers away, and in 2019 we had 120,000 visitors from the UK. So now moving to science and starting with the basics. Of course, for those of you who are not really spending all their day on all their time in particle physics, and then maybe more to move to more technical, some more technical slides. So our primary mission in science, what we do at CERN, we study the elementary particles. These are the building blocks of matters and of the universe. An elementary particle is an object that cannot be cut into smaller pieces. And we know that in the past people thought that atoms were elementary particles, but actually they were not, because we know today they are made of a central nucleus surrounded by a cloud of electrons. And then at some point nuclei were expected to be elementary, but they were not. They are made of protons and neutrons, and protons and neutrons are in turn made of quarks. And as far as we know today, electrons and quarks are elementary particles, so they cannot be cut into smaller pieces, and they are the fundamental constituents of matter. The matter that we know, the matter of which we are made, so the matter that we see in the universe is mainly made of electrons and quarks. In particle physics at modern accelerators, and CERN today runs the most powerful accelerator ever, the Large Hadron Colliders, allows us to study the fundamental laws of nature at the level of the quarks. So on physical scales of billions of a meter or smaller. And this study of the very, very small, the infinitely small, we could say, allows us also to understand the very, very big, namely the structure and evolution of the universe. So this is for the following reason. Today we know from experimental measures of increasing precision, and also from cosmology and from theory, that the universe had origin some 14 billion years ago from a big explosion called the Big Bang. At the beginning, the universe was very dense and very hot, and then with time it expanded and cooled down. At the beginning, it was essentially a gas of 3 elementary particles. So by studying the elementary particles and their interaction at the most fundamental level, we can understand how the initial universe behaved. And we have two complementary ways of studying the universe and its evolution and structure. One is to use telescopes in space or on Earth, and telescopes look and study the universe by studying the macrostructure, so planets, galaxies, stars, and by looking at the farthest objects, they can go back in time. However, there's a kind of wall behind which they cannot go, and this wall corresponds to 380,000 years from the Big Bang. Because for previous epoch, the universe was so hot and so dense that light could not escape. And so this light never could reach our telescopes. And so the main tool we have today to go to more primordial epochs of the universe is to use accelerators. And the way to do so is the following. So we use accelerators. Accelerators are typically housed in underground rings. You can see here a photo, a picture of the underground ring of the Large Hadron Collider. These blue tubes contain some elements of the accelerator. We'll go back to this later on. Accelerators are an ensemble, I mean, to oversimplify the picture, are an ensemble of electric fields which are used to accelerate particles incrementally at each turn. So at each turn, particles get a kick and they are accelerated to higher energies. And magnetic fields that are used to keep the particles inside the ring on the trajectory of the beams with a precision of a few microns, and a micron is a millionth of a meter. So these magnetic fields must be extremely strong and extremely powerful. So these accelerators are used to accelerate beams of particles in two opposite directions, and then to bring them into collisions. And in the collision, what happens in the collision? Well, if you accelerate, for instance, two beams of protons, we can imagine that in this big shock of the collision, protons go into thousands of pieces. This is not scientifically rigorous, but it's a way of explaining to the non-expert what happens. And so, because protons are made of quarks, as we have seen in a previous slide, bound together through other elementary particles called gluons, by smashing protons at very high energy, we can study the elementary constituents of protons, the quark and the gluons, and so understand how they behave. But also the energy that is produced in the collision can transform itself into new massive particles. We all remember E equal mc square, Einstein equation. So from energy and matter are the same form of the same quantity, the same entity. And so by smashing particles at the highest possible energies, we can produce very massive particles. And the higher the energy of the collision, the more massive are the particles that can be produced. And this is why the Higgs boson has been hunted for almost 50 years at accelerators across the world, and only discovered at CERN, at the Large Hadron Collider, because only the Large Hadron Collider had enough energy to produce the Higgs boson, which is a relatively heavy particles, at an unobservable rate. In order to study the collisions, and so what is produced at the level of after the collisions of the two beams, we use the so-called particle detectors. These are instruments which cover almost the full solid angles around the collision point, and are in principle able to detect, to measure the trajectory, the properties, the energy, and also to identify all the particles that have been produced in the collision. So we can assimilate the accelerators to giant microscopes that allow us to scrutinize matter at the level of not the human cells, as for microscope, normal microscope, but at the level of the quarks. And particle detectors can be seen as giant digital cameras which take pictures of the colliding beams. However, just to give you some numbers about the challenges of the LHC, the two LHC beams collide 40 million times a second, so this detector must be fast enough to analyze this collision very quickly and then decide what to do with this collision, whether to record them or to discard them because they're not particularly interesting. Now, the most powerful and ambitious accelerator ever is the Large Hadron Collider. So here you can see a nice view of the Geneva region. You can see in the background the Alps. You see Lake Geneva here. This white dashed line shows the border between Switzerland on the top of the screen and France on the bottom. Here you can see CERN headquarters, and this yellow circle shows the location, the position of the LHC ring, which is not visible on the surface. It's 100 meter underground and is a 27-kilometer ring. Operation started in 2010, and this opened the exploration of a new energy frontier, because the Large Hadron Collider allowed us today to explore energies which are a factor of 7 larger than the previous accelerator. This was the Tevatron Collider in the US. So operation means that since 2010 we have been, routinely accelerate 2 beams of protons in the 2 opposite directions of the ring, and we bring them into collision at 4 points of the ring, where 4 big particle detectors called ALICE, ATLAS, CMS, and LHCb have been installed in 4 big underground caverns. And their purpose, as I said, is to detect the products of the collision and then to interpret what happened in this collision, if a new particle was produced, if a new force was at play, etc. 2 years after the start of operation, on the 4th of July 2012, as Daniela already mentioned, ATLAS and CMS announced the discovery of a new particle, the Higgs boson, which is a very special one, and I will try to explain later on why this particle is so special. And let me also mention that UK laboratories, university and industry have contributed in a very significant way and continue to contribute in a very important way to all 4 experiments, to the accelerator and to the computing infrastructure. Actually, the Large Hadron Collider was approved in 1994, when the CERN Director General was Sir Chris Llewellyn-Smith, who is now currently Emeritus Professor at Oxford University, and we are very grateful to him for his driving action in getting the Large Hadron Collider approved. So the LHC required new concept and new technologies to not only make a big jump in energy, but also to develop the detector and accelerator technologies to be able to deal with the very powerful proton beams. So this is quite a spectacular view of the underground tunnel of the Large Hadron Collider. These blue tubes contain the backbone of the accelerators and perhaps the single most important ingredient that allow us to make a big jump in energies. And this is a set of 1200 high technology superconducting magnets. So in order to, in a hadron collider, so what is difficult is not to accelerate in a proton accelerator. It's not difficult to accelerate protons. What is difficult is to keep this very high energy beams inside the track of the accelerator, so along the accelerator circumference on a very precise orbit. And for that one needs very strong magnetic fields. And strong magnetic fields call for high current, and in order to produce high current without losses, one needs to use superconducting magnets, which essentially produce no resistance. Now, superconducting materials become superconducting at low temperature, and the LHC magnets operate in a bath of 120 tons of superfluid heliums operating at 1.9 Kelvin. 1.9 Kelvin means minus 271 degrees centigrade. And actually, the LHC is the coldest facility in the universe, because you remember I said at the beginning that the universe had origin from a big explosion. At the beginning was very hot, and then it cooled down, expanded. And if you ask yourself what is the temperature of the universe today, the temperature is 2.5 Kelvin, and actually the LHC operates at 1.9 Kelvin. A few other numbers: when the LHC operates at full capacity, there are something like 200,000 billions of protons in each beam, and the protons make something like 11,000 turns of the 27-kilometer ring per second, because they travel very close to the speed of light, and so on and so forth. The experiments, the detectors, are also extremely challenging and impressive. Here you can see a very nice and spectacular picture of Atlas, which is the largest of the 4 experiments, and a very strong group from Oxford University has been involved in Atlas since the beginning of the experiment. You can see the size of the experiments compared to 2 human beings. It's half the Notre Dame Cathedral in Paris. The other experiment, CMS, weighs more than the Tour Eiffel, just to stay in Paris, 13,000 tons, a factor of 2 more, and has more iron. But also, if you look at the core of this detector is made of 100 million of sensitive elements. And actually, the group in Oxford has developed one of the most challenging detector, the street detector, which is made of 6 million of silicon strip with a pitch of 80 micron. Is one of the core detector of Atlas. We need something like 3,000 kilometers of cables to bring the signal from the underground detector to the control room in the surface. And as of today, the LHC has produced in total data from the detector and data from simulation, something like 1 exabyte of data. So really impressive number. So the question is why? Why have we decided to embark in this quite challenging adventure? So very simply, for those of you who are not physicists, the LHC has been built to address some of the most important outstanding questions in fundamental physics. One of the question that has been with us for many years is related to the origin of the masses of the elementary particles, and this question has been answered at least in a large part with the discovery of the Higgs boson. I will get back to this later on, but there are many others. Today, one of the main focus of fundamental physics, not only at accelerator, but also cosmology, astroparticle physics, etc., is to understand the so-called dark universe. Because when we look at the sky in the evening, we see the nice star and galaxy. What we see is only 5% of what is out there, meaning that only 5% of the universe is made of the matter of which we are all made: quarks, electrons, and a few other particles. All the rest is made of forms of matter and energy that we don't know, and for this reason we call them dark matter and dark energy. And so understanding the dark universe is perhaps the most important obsessions of fundamental scientists today. And there are many others, and I will come back to this later. So the Higgs was discovered in 2012, and the Nobel Prize in Physics in 2013 was awarded to Francois Englert and Peter Higgs, who in 1964, together with other scientists, had predicted the existence of the Higgs boson, or to be more precise, had developed a mechanism called Braut-Englert-Higgs mechanism that allows the elementary particles to acquire a mass. And now, for those of you who are not experts, why is this so important? Well, because, as I mentioned at the beginning, atoms, of which we are all made, are made of electrons and quarks. And if electrons and quarks did not have a mass, if they were massless particles like photons, the photons are the quantum of light, then atoms will not stick together. So they will not exist as bound states. And so this implies that we will simply not be here. And so the Higgs boson has a very special role also for our own life. For the experts in the audience, on the other hand, I would like to show a few numbers and a few plots. The Higgs boson, once produced in the collision of the LHC proton beams, disintegrate itself immediately. It decays in other particles, known particles. For instance, it can decay in 4 leptons. So 4 electrons or 4 muons, 2 electrons, 2 muons. These are elementary particles. And you can see in this figure the mass spectrum of events containing 4 leptons in final states, as we saw it in 2012 when the Higgs boson was discovered. And you can see here this peak, which is very visible, but still we see many large error bars on the data point, around a mass of 125 GeV, corresponding to something like 130 proton masses, corresponding to the production of decay and the decay of the Higgs boson. And here today you can see the same plot. So the invariant mass of 4 leptons in the final states for events where 4 leptons were produced, and you see here a beautiful peak due to the Higgs boson. Of course, the difference between today and 2012 is, of course, that we have recorded many more data, much bigger data sample at the Large Hadron Collider. So not only that, but the ATLAS and CMS experiments since 2012 have been measuring the properties of the Higgs boson with increasing precision. Today we know its mass with a precision of a few per mil. We know the way it interacts with the other elementary particle, the so-called couplings, so the way it interacts to the photon, the W boson, the Z boson, and the quarks, etc. And also its spin zero nature, the fact that the Higgs boson is a scalar particle, has been established. Because the Higgs boson is related to the mechanism that gives mass to the elementary particles, it couples to the elementary particles in a way proportional to their mass. And now the fact that this is really the case has been experimentally measured. You see here the coupling of the Higgs boson to various elementary particles, and you can see that they scale with mass as predicted by the theory. So I'm now going to discuss a little bit the future, and I will try to be quite simple also for the non-expert in the audience. The elementary particles and their interaction are described by a theory which is called the standard model of the elementary particle. It's a theory which has been developed over the past 50 years thanks to very bold and great theoretical developments, but also many experimental efforts. The standard model predicts that the world of elementary particles is made of the object that you can see here. You see, for instance, particles that are called quarks. I mentioned them at the beginning. Particles that are called leptons. Among the leptons, we find the electron, which is very well known also in everyday lives. And there are particles that are called gauge boson, and these particles are responsible for transmitting the elementary forces at the most elementary level. So everybody knows, for instance, the photon, which is the quantum of the light, which transmit the electromagnetic force. But all the W and the Z boson, for instance, they transmit the weak force, which is responsible for the thermonuclear reaction of in the sun or for radioactive decays. The very nice thing is that all the particles that are predicted by the standard models have been discovered. The only missing piece was the Higgs boson, which was predicted by the theory of Braut and Higgs, and finally it was discovered in 2012. Not only that, but also we have tested the theory, the standard model, with very high precision, thanks to a large number of very precise measurements since the early 60s in labs across the world, in particular at accelerators, but not only. And the standard model works beautifully. So we could be very happy because we understand everything, but actually this is not the case, because there are many open questions, outstanding questions today, that are the results also of several experimental investigations that cannot be explained within the standard model. In other words, the standard model does not describe and explain everything. In other words, there is physics, there must be physics beyond the standard model. There must be what we call new physics, new particles, new interactions, new phenomena, which go beyond the standard model. And we are looking for this new physics. So why new physics? Well, I mentioned the dark universe. No single particles in the standard model can explain the dark matter and the features the dark matter has. So there must be new particles. We don't understand why there are 3 families of elementary particles here with different masses, with different behavior. We do not know why the universe today is mainly made of matter with very little antimatter. At the beginning of the universe, at the time of the Big Bang, matter and antimatter were produced in the same amount. We think then at some point nature decided the universe will evolve with a matter and will be only very little antimatter. Where did the antimatter go? We don't know, and so on and so forth. But the point is, in spite of these questions calling for new physics, for physics beyond the standard model, today we have no direct evidence for new particles. Of course, there are hints of deviation from the standard model at CERN and also in from other experiments across the world, but there is no direct evidence for new particles. So where are these new particles? Where is this new physics? Is it sitting at energy scales that are too high for us to reach with the Large Hadron Collider, in which case we need new facilities? So the main lines of research at current and future colliders proceed today along 2 lines. One line is the detailed study of the Higgs boson. The Higgs boson can only be studied at colliders. It can only be produced through colliding beams, and it's if you want, it's a very well established line of research, and it's also a very important door, if you want, into new physics. Why? Because the Higgs boson is not just another particle. It's profoundly different from all the elementary particles discovered previously. If you look, sorry for going back, if you look at all these particles, the Higgs boson has very peculiar properties, quantum numbers, we call them in physics, completely different from the other particles. For instance, for the expert in the audience, is the only elementary scalar we think is elementary ever discovered. It also brings a new type of force. For the expert, is a Yukawa force, it's not a gauge force. And also it's related to the most obscure part of the standard model. If you look at the standard model, at the theory, at the equation, you will see that the deeper structural questions and all the problems in the theory are related to the terms that involve the Higgs boson. So there is something profound with the Higgs boson related to our ignorance, and therefore studying the Higgs boson with the highest possible precision may give us clues for what goes beyond the standard model, what exists beyond the standard model for new physics. And the other line of research is to look directly for new particles and new phenomena, or indirectly by making many measurements of the known particles and phenomena and looking for the tiniest deviation from the expectation of the theory, which may indicate the existence of new physics. So what are the next steps? First of all, the Large Hadron Collider, which we are now running, and will operate until 2024. And then we will upgrade it through the so-called high luminosity upgrade to produce more brilliant and more intense beams of protons in order to be able to collect 10 times more data by the late 30s. And to do so, we have to upgrade something like 1.2 kilometers of the accelerator using new technologies, in particular developing a new generation of superconducting magnets based on a new material. The detector as well will have to be upgraded to be able to cope with the more intense beams, and in particular the group of physicists, engineers and technicians at Oxford is involved in the development of the new silicon detector for the ATLAS experiment. And then, of course, looking further ahead into the future, you know, the high luminosity LHC is an ongoing project that's been approved, and we are building it now. For the future, we are still in the design phase. No project has been approved, but one possibility would be to build a new collider similar to the Large Hadron Collider, but bigger. So you see here the Large Hadron Collider, 27-kilometer ring. We are thinking of a bigger collider, 80 to 100 kilometer tunnel in the Geneva region, which will allow us to make a big step forward in our understanding of the Higgs boson and in our searches for new physics, and in any case in our understanding of fundamental physics. Is a very ambitious project which will require pushing the technologies even more, and I will try to explain later on why these technologies are so important. China is considering to build a similar project, so if you want to retain in Europe the leadership in fundamental physics, in particle physics, and in the technologies that the field has developed, of course, it will be important to try to build a new collider here in Europe. So let me now move to a couple of final slides before concluding regarding the impact of CERN on society. First of all, CERN and industry. What do we develop with the industry in the member states, including the UK, and what do we buy from them? And you can see here the large variety of technologies that we develop with industry and we ultimately buy with them. The relation of CERN with industry is very peculiar. It's not just a client-provider, supplier relationship, it's more a partnership. So typically, because many of these components of our accelerators are so ambitious and the technologies are not known by industry at the time where we start to develop them, we usually build prototype in-house together with our industrial partner. And so we develop the technology through several prototypes. And once we are sure that we have understood and we mastered the technology, then the technology is transferred to industry. And then afterwards is the industry that builds thousands of magnets or thousands of machine vacuum elements or big cryogenic infrastructure and so on and so forth. So if you want, we grow together, and this partnership between a research infrastructure and industry is really very healthy and very useful, not only for science, but also for industry and for society. And second question, what does CERN transfer to society for free? So here you can see a few examples. Of course, the web, everybody knows the web, which was developed at CERN and has changed the way society accesses information. But there are other examples, for instance, in the medical field, medical applications. Today, there are various ways of treating cancer. One is to use the traditional X-ray therapy. And the other one is to use other types of beams using protons or light ions beams like carbon beams. The advantage of using these hadrons, and because protons belong to a family of particles called hadrons, so this therapy is called hadron therapy, is that beam of protons or light ions are really very much focused. So they do not spread, they do not just hit, they do not spread over the surrounding tissues, but they just can be focused to just hit the cancer. And so if you need to treat cancer that are close to very critical organs, you don't want the radiation to spread all over the places, you use then protons and light ions. Or if you want to treat cancer for children that you don't want to irradiate much, then you can use protons and light ions. But for instance, there are other examples, medical imaging. The PET scanner is one of the, today perhaps is the most widely used scanner in medical imaging. PET stands for positron emission tomography, and this scanner is based on detector technologies developed at CERN. And there are many examples, for instance, using dosimeter to monitor the quality of air for environmental application, or machine learning techniques which are used for car automation, and so on and so forth. So in conclusions, CERN today is not only a center of scientific excellence in fundamental physics, but it's also a driver of innovation for the development of advanced technology in partners with national labs, institute and industry in the member states and beyond, technologies that are transferred to society with important impact on health, environment, energy, computing, superconducting materials, just to name a few. It's also a place where we train the young generation of scientists, and we try to attract talents to the member states from all over the world. It's also a bright example of inclusiveness and collaboration across borders, and actually the CERN model for cooperation across borders and our governance model. How is it possible to have, to make 18,000 scientists from all over the world working together and being able to deliver a giant accelerator, giant detector, big computing infrastructure. So this CERN model has been studied by the UN also, but also exported to other facilities. Like a very bright example is also Sesame, the synchrotron light for experimental science and application in the Middle East, which is a facility in Jordan for fundamental research and application that brings together some of the local actors, which we know very well are not the best friends of each other. And CERN is also a great promoter of open science. Open science, developments, results available to everybody is enshrined in our convention, which again speaks of the vision of our founding members. Open science means publishing our results in open access journals where nobody has to pay for reading. Our data are available to everybody, developing open source hardware and software, making our technologies and our education accessible to all, also as a means not only to promote science, but also of reducing inequities across the world. So if you want, CERN is not just a world-class scientific center, but in my opinion, also a value system. Thank you very much.
Thank you, Fabiola, for the fantastic lecture. And I want to give you a standing ovation, by Zoom, okay? I don't know how to say
thank you
for everybody in the room, okay? We have a lot of our audience who has typed a question in the question and answer point of our web, of our Zoom window. And so I would like to ask you a few questions in their behalf, okay? I start actually with two questions. I will try to combine them actually. And one of them come from a young inspiring scientist, Will, who is age 13, and he asked us how, as a particle for the accelerator being produced, and I wanted to combine it with the question of somebody else, which was, what is the source of protons?
Okay, very good. Thank you for the very good question. The source of protons in our accelerator chain is just a bottle of hydrogen. As you know, hydrogen is the simplest element, is the lightest element. Its nucleus is just made of a proton, and then there is one electron orbiting around the proton. So what we do, we take a bottle of hydrogen, we strips out with the electrons, and we are left with the gas of protons, and then we accelerate through our accelerator chains. Actually, I didn't have the time to go into details. I just mentioned the Large Hadron Collider, but the CERN accelerator complex is made of several links of several accelerators, some linear, some circular, and the protons are accelerated through several steps, thanks to these different links in the chain, but also the structure of the beams is shaped in terms of time structure, in terms of technical characteristics of the beams before being at the end injected into the Large Hadron Collider, where they are finally accelerated to reach the collision energies.
Okay, continuing on the acceleration of particle, you mentioned that it's not so difficult to accelerate proton. Why is it so? It has a significant mass, so its acceleration should have been difficult. And the couple question, I'm trying to do always the 2 questions so that we address more people, is what is the source of energy for accelerating the protons in the LHC?
Okay, thank you very much for the question. So first of all, protons are not difficult to accelerate because the energy that you use in the acceleration is not lost. So it's true, you have to accelerate them by giving them a kick at every steps. However, the protons do not irradiate that energy, and so, or very little, and therefore the acceleration process is very efficient. This is different from electrons. So that's why I said that with proton beam in a proton accelerator, the difficult thing is not to accelerate the particles, but then of course to keep them in the trajectories. Electrons, on the other hand, are more difficult to accelerate because they irradiate energy. So at some point the process becomes inefficient because you continue to pump in energy and this energy is lost. So that's why it's very difficult to reach a very, very high energy with electrons in rings, in collider rings. Of course, you can do so in linear colliders. So that, and then for the other question was, yes, on the energy which is used, electricity actually comes from EDF, Électricité de France. So CERN electricity supplier, which is used to feed all our and to power all our instruments, from the accelerators to the cryogenic plants, etc., come from currently from EDF, which is the electricity supplier of France. Of course, every few years our contracts are adjudicated through a competitive process, process in the member state countries, and of course at the next round it will be another energy supply.
Okay, several in the audience have heard about the G-2 result, and they're wondering what is the implication of this result on the standard model, for example, and you know.
Yeah, of course. It's when I mentioned en passant, in passing, at some point that we have no evidence of new physics in the sense that we have not observed particles today beyond the standard model. Nevertheless, there are a few hints here and there. Actually, I was alluding to G-2 or also some other anomalies that the LHCb experiments has observed at the Large Hadron Collider. So it's a little bit early to say because these hints did not reach really the statistical significance that is required to claim a discovery. So we will need to accumulate more data. We will need to look also at other complementary processes to understand if the anomalies that we see in some channel like G-2 or in some the case of the B mesons at the LHB experiments are really are really present also in other processes. But clearly, if these hints are confirmed, they may signal the existence of physics beyond the standard model. If they are confirmed and they persist, and if their precision becomes pushes them to become a discovery, and so with no doubt, then clearly there is no way we can explain this in the standard model. It means new physics. Now, understanding the nature of this new physics, that's another question, but of course it would be a very intriguing and exciting things to do, of course.
Well, connected with this question is what is the current state of the search for supersymmetry and supersymmetric particles?
So I must say that this is a very good question, and of course I'm very happy to reply to this question, but also I would like to make a comment afterwards. So search for supersymmetries have been carried out at the Large Hadron Collider and also at previous colliders now for many decades. We have no hint of the existence of supersymmetric particles, and so what the experiments have been doing so far is to exclude at least some classes of supersymmetric models, or masses of supersymmetric particles in the mass ranges up to a few TeV, if you want. Well, 1 TeV or so, 1 to 1.5 TeV, say, maximum for pair-produced particles. Now, the thing I would like to stress is the following. First of all, this does not mean that supersymmetry does not exist and that supersymmetric theories are wrong. This may just mean that TeV-scale supersymmetry does not exist, but supersymmetry has a theory, can exist at a very high energy scale. Is actually an element of string theory. So it may exist at energy that we will not be able to reach with our accelerator. The second thing that I would like to stress is that what we are doing at the Large Hadron Collider and with our experiments is not to run behind a given theory. It's not that we are here to disprove supersymmetry or to look for supersymmetry or extra dimension or leptoquarks or many other models of physics beyond the standard model which have been developed by human beings. We are here to address the outstanding questions. So we are here to try to answer the question like where did the antimatter go? What is the composition of dark matter? And of course, the answer to the composition of dark matter could be the particle that makes up dark matter is a supersymmetric particle. That then would be nice for supersymmetry, but maybe nature has chosen another solution for dark matter. So we have to remain with a very, very open-minded. The experiments are extremely flexible, extremely versatile. They have technologies at the level starting from what we call the trigger, so the online selection of the events, which are extremely open, exactly to be able to not only discover known, let's say, theories that have been developed by theorists, they may be true or not, but also to be open to any other signature or any other models that or the truth that nature has chosen.
Yes, again, a little bit on this vein, several have asked if there are experiments that are specific to look for the graviton.
Well, there are, yeah, so graviton, TeV-scale gravitons are being looked by the two general purpose experiment, ATLAS and CMS, because of course, gravitons may manifest themselves like, missing energy in final states because they do not interact with the detector. So searches for events containing large missing energies for the expert in the audience is also a way for looking for gravitons. So yes, the two general purpose experiments are also looking for TeV-scale gravity.
Okay, so another question was asking about if you can give us a loose time estimate for the FCC. And in more general terms, how do you see the future of particle physics? Okay, so maybe now I should go back. Well, I will not share any slides, perhaps I will say just in words. So the FCC has quite a broad program because it will be a new tunnel, and this tunnel could host initially any plus and minus collider, electron-positron collider, followed later on by a hadron collider for proton-proton collision, but also heavy ion collisions. This is what we did in the past with the current tunnel. We had a lab in the 90s, the previous electron-positron collider, and then we had the Large Hadron Collider. So now, clearly, the time scale will be very much determined by the funding also that we can find for this accelerator. If we look just at the technical schedule, so technically speaking, when we should be able to run the first stage of the FCC, so the electron-positron machine, this may well be the early 40s. We are going to complete the high luminosity LHC in 2038. In parallel, the idea will be in parallel to start digging the tunnel, say, in the early 30s, if everything goes well. Of course, if the project is approved, if with 100 ifs. So if this goes ahead, then we should be able to start digging the tunnel in the early 30s. And the electron-positron collider, it's a machine for which, of course, we need
advanced technologies, but is a machine that we think we can build by the time scale of the early 40s. And this will be very good, because then the gap between the end of the high luminosity LHC and the beginning of a future facility will be less than 10 years, which is, I think, very healthy for a lab like CERN. 10 years is more or less the gap between the end of LEP and the beginning of LHC. And of course, then for the next step, the Hadron Collider, this is yet another important step. First of all, because it's Hadron Collider is much more expensive. And because we need to build new technology and new generation superconducting magnets, but also because the technologies today are not yet there. I mean, for the current for the high luminosity LHC, we are developing these new niobium-13 magnets with fields 11, 12 Tesla. For the FCC, we are talking about 16, 20 Tesla. So is yet another step, is developing also, implies developing also high temperature superconductors. So the technology is not yet mature. So for Hadron Collider, I will see 2060s or so.
So it's a long road, but again, going back to the experiments that we are taking now, there was a question that is quite interesting, because they were wondering how, there are a lot of scientists working on the LHC. You gave the numbers of the Atlas collaboration and CMS. With such a large team, how does the process go from collecting the data and processing the data and announcing, on July 4th, announcing the discovery?
Oh, this would require a full lecture of the sociology of this collaboration, which actually have been studied, still are studying by sociologists. A few theses, PhD theses have been made by sociologists about the way we operate, and also we have been examined by businessmen, corporates, etc., to understand how we. So, of course, I cannot go into the details, but I will say, yes, it's a kind of miracle that if you take an experiment like Atlas, for instance, Atlas, just choosing one randomly, Atlas is a collaboration of 3,000 physicists from all over the world. Okay. Some 40 countries. And if you look at the Atlas detector, I've shown this spectacular picture, is extremely complex, extremely ambitious. And there is no single components of this detector which has been built in a single country. All of the components are the results of the collaboration of engineers, physicists, and scientists sitting in different countries. And for me, it's a miracle when you put all the pieces together, they match, because, with so many people, of course, we have a strong engineering, we have strong, we are super well organized. But to come back to your question, I think that, first of all, there is one important principle, and this is, I think, the reason why it all works so well. We are all animated by the same passion, and we all have the same goals, and the goals is discover the Higgs boson, find new physics, improve our understanding of how the universe works, etc. And this and the awareness that there is no way that we can do so alone. We need the collaboration of all the involved people. So when there is such a strong focus, a strong glue, this also helps, surmounting possible dispute, for possible incompatibilities of characters, because of course you can imagine 3,000 physicists, they are not all going along well together with each other. But this is one important thing. The other important thing is that this collaboration, they do have some managerial structure. Of course, otherwise we will not be able to produce the results so well, so quickly, to build this complex detector. However, this structure is relatively light. Bureaucracy is minimized because we are doing research, and research is based on ideas, and ideas require creativity, require freedom. And what is nice in this experiment that is, if the younger student has a a bright idea on how to solve a problem or how to improve an analysis, on how to build a new piece of detector, then the collaboration follows. So the hierarchy does not come from the bosses, it comes from the ideas. And this is, I think, very motivating.
That's a very nice answer. Paolo, can we ask a few more questions, or you know, you are the grand maestro of ceremony.
Master of ceremony.
I really
say
feel
another couple of questions, Daniela, and okay. I would like to take the opportunity to say hello to Chris Llewellyn-Smith, who is in the audience. So previous Director General of CERN. Yes, hello.
Hi, Chris.
Hi, Chris.
But ask a few questions.
Actually, I must say that Sir Chris is the Director General who hired me at CERN. So I'm at CERN thanks to Sir Chris.
Very nice. Fantastic. One a little bit provocative, perhaps, question. Okay. Is LHC really needed to develop hadron therapy or various methods of medical imaging? I mean, it sounds very good that it came from CERN, but is really true, or is more of a selling point? This is a bit of a tricky question.
No, I think it's true. It's true that the technology, the accelerator technology for hadron therapy, in particular for light ions, but also for protons, was initially developed in our field. And essentially all the applications to nowadays that have in industry, accelerators are widely used in industry as well. They originally come from the field of particle physics. The question is, would they have been developed also without the big research infrastructure? I don't know, maybe yes, maybe not. But you know, there are some technologies that sometimes really require the impetus, the boost of fundamental research to be developed quickly and also then to be shared with everyone for free. Take the web. If Tim Berners-Lee had not developed the web at CERN, sooner or later someone else will have developed the web at the end, I think, maybe a few years later. But you know, the advantage of CERN developing it was not only that it was done, it was pioneered here, and the idea came from here, but also that it has been made available to everybody for free. If it had been developed maybe by a private sector company, every time you click, you would have to pay, which is not the case with that. So, you know, the advantage of technologies developed in fundamental research, which are funded by public money, is that they are available to everyone without royalties.
Very big advantage, isn't it? Yeah. What is the next big discovery we can expect in particle physics in the next 5 years? And will quantum computing accelerate research?
So what is the next discovery we can expect? I have to be frank. I have no idea. I don't know. Exactly because we are, as I said before, we are trying to address such number of questions, and we don't know where the answer to this question is and what the answer to this question is. So, you know, we may, you know, discover the particles that make up dark matter. We can find additional hints in flavor physics, like the one from LHCb, or some deviation for the second generation of particles like G-2, and now also the LHCb RK measurement. I have no idea. What I can say that it will continue to look for answers to things that we do not know today. And concerning quantum, yes, of course, we can expect quantum technologies to accelerate the field, not only our field, but also other field, quantum sensor, quantum computing. We are still far from there, so we have to. We are at the beginning of the journey, but for sure, one day we will be able to use quantum technology in the best possible way to the advantage of the field.
So now,
and sorry, Daniela, to interrupt you, and I think again that the field may also play some leading role also there. And I'm trying to explain why. Now quantum technologies or quantum computing are being developed by several institutions, including private actors, of course, private sectors. So And we have a strong partnership here at CERN in the so-called Open Lab between research in the member states and at CERN and the industrial partners. So why the industrial partners, for instance, in quantum computing, they are so much interested in working with CERN? Again, because the physics and the science we do is so ambitious. The algorithms that we develop are so advanced. The problems that we have to solve are so complex that we are an excellent use cases for industry. And so this is an example of how partnership between research and industry, again, can be harnessed to the advantage of developing technologies quickly.
So now I'm going to ask you the last questions that come from Nina. What about CERN makes you happiest? What are you proudest with? So this is the last question.
Thank you. It's a very nice question, Nina. Thank you very much. I think I could say the discovery of the Higgs boson, in which I've been involved in. I could say many other, I think, but no, I think I would like to answer in the way I concluded my presentation. I think today CERN is a value of, it has always been, CERN is a value system. Is a place where people work together in an open way. It's a place where there are no barriers. It's a place where your ethnicity, your passport, your religion, your political party, whatever, doesn't matter. It's a place where we try to, if you want, we try to plant little seeds of peace. Of course, we cannot solve geopolitical conflicts. We can't, but we can plant little seeds of peace and of and showing that there are good values and that can promote good values. So this is what makes me mostly proud of CERN. And I keep thanking our founding fathers for the marvelous things they've done and their vision back in 1954.
Thank you, Fabiola. Again, my virtual clap, and I pass it to Paolo.
And thank you very much, Fabiola, and let's hope that these little seeds of peace will blossom and grow into big trees. And with this, I think we shall conclude the lecture, and thank you, the audience, for having been with us and with the physics department today. Thank you.